Okay, let us get started. So, we had looked at the basics of modeling time constant before, different types of timing constants and modeling, and we had seen some little bit of scheduling terminologies. Now, let us get started from that point. So, the basics of real time task scheduling, and as we proceed we will look at sophisticated task schedulers, starting from very simple task schedulers to more and more sophisticated schedulers. It is not that the simple ones are not used, the simple ones are the one that is used maximum, because many small devices exist, but the complex one are also used. So, we need to look at those various types of task schedulers. So, these are some of the terminologies we had looked at, like a task is released or arrived when the task is generated due to a event, and then we had said that scheduling is an important problem, possibly one of the most important component, possibly the most important component of any real time operating system. And we are looking at these terminologies of task instance. A task instance arises again and again, new instances occur as events keep on happening, and we said we will denote the ith instance, ith time the task recurs by Ti. And then we were discussing about the absolute and relative deadlines. This is a term we will use quite often. Absolute deadline, whenever we will tell, will mean that it is with respect to time 0, that deadline is measured with respect to time 0, whereas the relative deadline is with respect to the task release time. And response time we had discussed, this is also a terminology in traditional operating systems. The time a task starts, actually released, this is the time when the task actually starts executing. So, the time the task is released to the time, and the time the task completes and produces result, that is the response time. So, one thing that possibly we can say here, just to clarify the questions that you were asking, that response time is actually not the characteristic of a task. Response time is the characteristic of an event. So, the characteristic of the event, that is sort of the heater, is the event, right. So, this event is generated by this task. So, the response time of a event or a action taken by the system, that is the response time. It is not proper to say that response time has with respect to a task, not a very proper way to tell that. The proper way is that the event generated by the system in response to this, what is the response time, right. For this event heater sort of, the response time is this. If the task generates some other events as it executes, possibly the response time of those events, right. I hope that answers the questions that we are asking, that it would not be proper to, I mean, for this simple case where the task completion is coincident with the response event, we can say that the response time is this one, the task completion time, but the event can also occur as the task executes. So, those the response time of those specific events we will have to talk of. It is not except for the simple tasks, we will not associate response time with more complicated tasks where events keep on occurring, right.
Sir?
Yeah, please. Yeah, please.
The response time is till the completion of the action by the system, sir, or just recognition of what action has to be done?
No, see, we are not really talking of actions here, we are talking of events generated by the environment and events produced by the system, right. So, once the event is produced by the environment or maybe with respect to system, that is a stimulus response event or a response event, we will talk of the response time. The response event, it is a event, not action actually. For example, heater sort of signal is generated. It is not that when exactly the heater becomes 0 degree or something, the sort of signal was produced, that is an instant of time. So, we will talk between two instants of time, okay, two events,
So
instantaneous events.
The response time will be from temperature becoming greater than
Sense to high, yeah,
and the heater shut off.
exactly,
completely.
exactly. But for this simple example,
Sir, if the case is like that, the event generated by the system in response to the event, if that is a durational event, like it is not instantaneous,
okay.
it has got some duration.
Okay. So, then we will have to associate that when the duration event, see his question is that what will be the response time if the system produces a durational event. So, in that case we will have to again, like we were doing earlier, associate when the duration event started and when the duration event ended. So, we have to consider those things, the points of time, the point at which the duration event started and the point of time at which the duration ended. So, we will have to, the response time will not be a very simple answer there. For some cases, we will say that the response time is when the duration event started. In some cases, we will say that it also depends on when the response event ended, right, the durational event ended, right. For the simple case that we are talking of, where a instantaneous event occurs by the system in response to some event, either a stimulus event or a response event, we are saying that that is the response time. So, response time is associated with the event, not with the task. But for this simple case, where the event coincides with task completion, written this as the response time for the simplest case. Is that okay? For a soft real time task, the objective is to minimize the response time. That is, let us say if you are pressed a keyboard on a computer, what happens is the operating system recognizes it and then shows you back the character on the terminal, is not it? So, if you press the key, the character does not appear on the terminal, you say that it is not very responsive. But if it is able to schedule the tasks such that you can immediately see your response to the, you press the key, immediately appears on the terminal, say that the system is very responsive, right. So, that is the traditional terminology, but here in the traditional operating system was that we minimize the response time, but here what we are saying is that minimizing response time holds no advantage. We will not minimize the response time in all the schedulers that we will consider. We will just try on completing all the tasks within the deadline, that is the main objective here. And then we are looking at the three categories of tasks that are common in a real time situation, the periodic ones, and we are saying that in some systems all the tasks are periodic, and in any system majority 99% or something tasks will be periodic. Sporadic tasks, these occur at random instance, and aperiodic similar to sporadic, but the minimum separation between task instances is 0. And we are also discussing about the phase is the time that elapses before the first instance of a periodic task starts, and then it keeps on recurring with some period. So, we will use the term phi to denote the phase of a periodic task. So, for a task Ti, we will use phi I as its phase. And we are also looking at the terminologies valid schedule and feasible schedule. So, some of you just remarked that a feasible schedule is also a valid schedule. Yes, a feasible schedule by definition is a valid schedule. And then a proficient scheduler, a scheduler S1 is more proficient than another scheduler S1, S2 if S2 can feasibly schedule sorry, if whatever feasible schedule produced by S2, S1 also can produce some feasible schedule for that given a set of tasks. If S2 produces a feasible schedule, so also can S1, but there will be some schedule, some set of tasks for which S1 can feasibly schedule, but S2 cannot. So, that is why we are saying that S1 is more proficient than S2. Equally proficient, we will also use this term that for whatever task situation, S1 can produce a feasible schedule, so can S2 and also vice versa. And we also discussed about an optimal scheduler, where if there is any scheduler that can produce a feasible task, a feasible schedule for a set of tasks, so can the optimal scheduler. So, not saying that the optimal scheduler will try to schedule any set of tasks. No, if some other scheduler can do, so also can optimal scheduler. That is the terminology. Okay, let us proceed now. Another very important term we will use almost every time we talk of a scheduler is the scheduling point. Actually, these are points in the time at which the scheduler will try to find out which task to take up next. So, the scheduler does not run all the time, right, it runs at specific points of time as the computation proceeds, and at that points of time it wakes up and tries to decide which one to run next. So, that is a scheduling point, the specific points in the time at which the scheduler becomes active and tries to decide which one to run next. In a clock driven scheduler, this is the terminology we will use, in a for those scheduler where the scheduling points are defined by interrupts from a periodic timer. So, every time a timer interrupt comes. So, the timer is a periodic interrupt, periodic interrupts come from some timer, and each time the interrupt comes, let us say 10 millisecond or maybe 100 millisecond, the scheduler wakes up and tries to find out what to do next. So, that is a clock driven scheduler. On the other hand, we will have another category of schedulers, where the scheduling points are defined by some events which are not really clock events. Here, let us say a high temperature is sensed, or let us say a fire condition is sensed. So, the events need not occur according to some clock, and once the event occurs, task needs to be released. At that time, the scheduler wakes up and tries to find out what to do at that time, which task to take up, and also when a task completes, the scheduler also wakes up. So, the scheduler does not wake up really periodically, it wakes up as and when required, when a new task arrives or some task that is executing completes. Okay? So, that is the basic difference between a clock driven scheduler and a event driven scheduler. These are two main categories of schedulers that we will be discussing. As we are saying that lot of research has happened, has been reported in real time task scheduling, and if we look at all that research reports that have been published, mainly there are two categories of those schedulers. One is schedulers for uniprocessors and the other is for multiprocessor and distributed systems. We can classify them into two categories. Now, let us try to look at task scheduling in uniprocessor, because this is a much simpler problem. We will see that multiprocessor and distributed task scheduling is much more involved, many issues there actually. Here this is the simplest one, and if you look at the research results, most of the research occurred here during 1960s, 70s and 80s, and after that the intensity of research for uniprocessor scheduling has really reduced, excepting for finding uniprocessor scheduler for special type of task situations. But in general you will find that new schedulers are not appearing for uniprocessor. Why is that? because optimal schedulers have been found in these cases, whereas multiprocessor and distributed we do not have an optimal scheduler, right. Now, let us see this. So, the schedulers for uniprocessors can be broadly classified into clock driven and event driven, as we were saying that two main categories of schedulers, the clock driven ones and the event driven ones. And in each of these thousands of papers have been published, many variants, especially in the event driven, thousands of PhD degrees have been given, thousands or tens of thousands proposing new types of event driven schedulers with small difference in characteristics and so on. So, we will not really go into all that result, but we will go into the results which is enough to understand this area well, uniprocessor real time task scheduling. First, let us look at the clock driven schedulers, because these are the simplest ones. The event driven ones are more complex. So, here as we are saying that there is a timer which produces interrupts at regular intervals, and each time an interrupt occurs, the scheduler wakes up, and that is the scheduling point. And here normally we will see that there are variations of this actually, but typically the schedule will be stored in a table, right, in a clock driven scheduler. So, for the scheduler nothing too much to do actually. As soon as the clock interrupt comes, it just checks which has what is the status of the task that is executing. It does not even have to do that actually. It just looks at the table and finds out whether the current task needs to be stopped and the next task needs to be started. Okay, do that. It is a very simple thing. So, here we will have a table where we will store the schedule. So, the schedule is pre-computed in a clock driven schedule. We will store it in, we will pre-compute and store it in a table, and as the scheduler runs, the clock driven scheduler, regularly it will check the table and see what to do. And there are two popular examples of clock driven schedulers. We had said that there are many types, but two which are sufficient for us to know, I mean very popularly used, most of the applications you will see that these are the two they are used. One is a table driven scheduler, other we will call it as a cyclic scheduler. The one that we discussed in the operating system course, round robin scheduling, time sliced round robin scheduling is also an example of this, right. We have time slices, and at the clock interrupt, according to clock interrupt, the time slices occur, and after time slice one task is next task is taken up, and that occurs in a round robin, right. So, that is an example of a clock driven scheduler. So, we will discuss these two, the table driven scheduler and the cyclic scheduler. And these are also called as offline schedulers, because we would have to somehow develop the schedule of the tasks and store that in a table. These are offline because they are not decided, the schedule is not dynamically decided as the system proceeds. That is why this is also called as static scheduler. Offline scheduler and static scheduler, two terminology we will use to refer to these clock driven schedulers. The concept is very simple, but used extensively in embedded applications. Actually, I visited some of the industries which manufacture embedded applications, and I just talked to them what kind of schedulers do you use, what kind of operating system and scheduler. They said that, see, we use only clock driven scheduler because our applications are simple, do not need anything beyond that, most efficient, simple, you can manufacture devices cheaply which produces the desired result. So, very important category, even the simple, very important. It is likely that if you work in embedded industry or where real time programming goes on, you will mostly be using this. So, let us look at this. The main advantage is that these are very efficient, take very little space. The scheduler component is nothing actually, just consult something and just finds out whether to stop the current one, start the next one.
But the table will take extra space.
Okay. So, yes, space is a problem here, because we need to store the schedule, whereas in the other schedulers, the event driven ones, we do not store the schedule, but we will use space there for other purposes. We do not store the schedule there, but we will anyway use space to store the tasks that are pending, all those, right, what have not completed so far, but here there is no such concept, just keep the schedule and keep on taking one out of that. So, very computationally efficient, nothing much to do for the scheduler, checks up the schedule table and just does as is there in the table. But the work is that we have to somehow produce that table, right, let us see. And of course, minimizing that table is an important problem, because for embedded applications you can't really store a table which is several megabytes, takes several megabytes. Another, one big problem here, why clock driven schedulers are not used in unless the application is really small, is that cannot handle sporadic or aperiodic tasks, very difficult here. Only the periodic tasks can be handled. Even for a cell phone, we were discussing the example of a cell phone, there are some tasks which can be periodic, but most of the tasks there, many tasks, for example, the user pressed this thing, sent a SMS, set up a call, those all are aperiodic, is not it? Okay. So, table driven scheduling stores a table, as we said. The table contains the schedule. So, if you have 3 tasks, the task 1 will start at 0 time and it will be stopped at 100. T2 will start at 101, continue at 150. T3 starts at 151 and stop at 225. Typically, the scheduler what it will do is start the task 0, set a timer, and as the timer interrupt comes, it will take up the next one, right.
Even if it is not completed in the
Yeah, even if it is not completed, yes, that is the difficulty with this. So, if for some reason it cannot complete by this, it will be just stopped, started the next one, that is all. The scheduler just consults the table, whatever is there in the table, it just does that. No.
Deadline for task even then.
So, that in the offline we will have to do that. So, it is unto the designer, it is nothing to do with the scheduler. The scheduler will do whatever is stored in the table. So, it is the programmer, the designer who is the one who will produce this schedule. Yeah, we will see how to do that. Okay. So, for each task, for each time we will have to set up a timer, and now let us say if we have n tasks, then the scheduler develops a permanent schedule for P1, P2, Pn LCM. Why is that? See, each task, n periodic tasks, and let us say T1, T2, Tn. So, the tasks are T1, T2, Tn, and their corresponding periods are P1, P2, Pn, or in other words, task T1 starts at 0 and keeps occurring at P1 interval. So, first one is at P1, 2 P1, 3 P1, and sometime during this period it just starts executing and completes sometime, but before the end of the period, right. Now, there are other tasks like that, P2, 2p2, three p2 and pn. Now, what we are saying is that what is the size of the table for which the schedule needs to be stored? Should we store up to pn? Will that be enough? What do you think?
Between again T1 so
No, see, can we store the entire schedule starting from 0 up to pn? Let us say this is pn, the nth task is 0 to pn, let us say pn. Will this be enough? If we store 0 to pn, will this be enough? No. Why is that?
Some of the tasks gets partially completed by time.
Yeah. So, let me just draw another diagram. Let us say, let us consider two tasks P1 and P2. So, P1 let us say occurs like this. Okay, here let me draw like this. This is P1, 2 P1, 2 P2. Now, let us say 3 P1, I am sorry, P1, 2 P1, 3 P1 from time 0, and let us say this is P2. Then 2 P2. So, is it okay if we store the schedule up to P2? So, when P1 runs, first instance P1, second instance of P1, and then when P2 runs, is that enough to store that? No, obviously, because what do we do when the next instance of P1 occurs? Right, it is not repeating from here. Okay, so, we need to store the table, the schedule table, until all of them have 0 time of, see here it was 0, right, it was 0, and the situation that occurred in 0, that same situation must occur at the point up to which we need to store the schedule. So, when will that situation occur? It is the LCM, just think of it. So, that is the least common multiple of all the periods at which the situation is as if all of them are starting again from 0. Or in other word, we must store the table up to a point of time such that that time divides all the periods divide this time. If we store up to t, then t by pi should be an integral number, and the lowest that we can do is the LCM, right, lowest common multiple of all the periods. So, that is why I have written here that for a periodic scheduler, for a table driven scheduler, we need to store the table size up to this time, for the time LCM P1, P2 up to Pn, right. And then the schedule is taken up one by one, timer is set and handled, and then it is repeated forever. After the table ends, again start from the beginning. This is a very simple scheduler, nothing much for the scheduler to do excepting consulting the table, and as soon as the table ends, start from the 0. Very efficient, nothing much to do, very little runtime overhead, can have just few instructions. But main problem is that it is inflexible, very difficult to accommodate dynamic tasks. Now, see, one thing is that we will have to do a large number of timer settings here, right. Each time we set a timer, right, sometimes for 100, sometimes for 150, sometimes 70. So, this is a major problem here for this table driven scheduler. Each time we need to set a timer. Now, can we do better? So, let us look at that. So, we have the cyclic scheduler. Actually, if you go to a embedded industry, find that this is the one, the cyclic scheduler is the one which is extensively used, not the table driven one, because of the reason we said that each time. Now, this occurs in millisecond, and millisecond you set a timer, just imagine the efficiency issue, right. Here you do not set any timer. Let us see the cyclic scheduler, no timer setting will be necessary. Extensively used, almost any real time, small real time development you want to do, you will use a cyclic scheduler. Large majority of the small embedded applications use these cyclic schedulers. So, let us look at it. Here unlike the table driven scheduler, we do not store it for a period, the entire period of LCM of something and then keep on repeating. Here what we do is, we also actually we store a schedule here also, but the schedule we divide it into two parts, the major cycle and the minor cycle. The major cycle is the one which repeats, the schedule repeats in the major cycle, right. We have some diagrams to show you, and each major cycle is divided into minor cycles, and the minor cycles we will call them as frames. AK for also known as, yeah, right. AK is also known as. So, these are equivalent term. A minor cycle also known as a frame. So, a major cycle is there, which is the period for which the schedule is stored, and then the major cycle is divided into minor cycles, and a task can start either, not either, it only at the start of a minor cycle. It cannot start anywhere. See, in the table driven scheduler, the task can start anywhere at 100, 150, anywhere. But here it will, let us say task, it will either start at 10 or 20 or 30 or 40. If the frame size is 10, then it has to start a multiple of 10, right. So, there is a major cycle, after which again the schedule is repeated, and each major cycle is divided into equal sized minor cycle called as frames. And we can, the scheduler wakes up only at the start of a frame. See here, no setting of timer each time is necessary. We have the scheduler waking up only after every frame, it does not set any timer anytime, is not it? Basic difference between a table driven and a cyclic scheduler. So, see this, that the major cycle, the tasks are repeated here, the schedule is repeated. See here, this one was running here, this one is running here, then the red one, yellow one, etc. So, the schedule is repeated in each major cycle, but the major cycle is divided into these minor cycles, and the tasks can start at a minor cycle or the beginning of a frame, but it can end before a frame. So, some time may be wasted, nothing is running here, because the task started at a minor cycle or a frame, but could use only few frames and part of one frame. This much is wasted, but in a in a table driven scheduler, as soon as this completes, we could have started another one. So, that way possibly it uses the processor time less efficiently, but it has a major advantage, no timer setting is necessary. So, the major cycle again can be given by P1, P2, Pn. We will see that we also sometimes need to change this, we will see situations under which, and then this will occur even when the tasks have arbitrary phasings, right. We know what is a phasing. So, if P1, P2, Pn are the periods of T1, T2, Tn, then we had said that the schedule will repeat after this. I mean, normally we will see some situations where we need to store slightly larger if we have not designed our scheduler properly, but I mean the cyclic scheduler. But this is the one we can do best. We can reduce the major cycle below LCM P1, P2, Pn, isn't it?
So here also we will have to set at least one timer for the major cycle.
No, no timer is set for major cycle.
How does the system come to know if one major cycle is over?
See, it just keeps on checking the table, right. Each frame, at the beginning of a frame, the timer interrupt comes, the scheduler awakes and then it tries to see what is there in the table. As soon as the table ends, it takes up the next from the beginning.
The beginning
No
it has to
timer
be
is set.
Means first only once it has to be set.
Yeah, I think that is a good point. He says that in a cyclic scheduler, we need to set a periodic timer only once, right. It is a good point that the cyclic scheduler, a periodic timer, let us say 10 millisecond or 15 millisecond, as we will decide on the frame size, a timer is set only once, which demarcates the frame boundaries.
Frame boundaries or the major cycle?
Major cycle we do not bother. Major cycle will store the schedule up to the major cycle, but no timer setting is necessary for a major cycle. We only set one periodic timer, as he said, which gives interrupts only at the frame boundaries, and we keep on tasks one by one from the table, keep executing them each frame, and then as soon as the schedule ends, we start from the beginning.
So does it mean that we will have to set the timers for each of the frames at least?
No, that is a periodic timer. See, as we discuss into more detail, that in any operating system, there are two types of timer. One timer is a one shot timer. A one shot timer is where we just set it once for 100 millisecond. After 100, it just gives one. A periodic timer is one where we just set it once, that every 50 or every 15 or 10, you just give us a interrupt. It just keeps on giving every 15. We do not set it each time. Set it only once, keeps on giving interrupts. Is that okay? So, in that way it is much more efficient. Only one setting is necessary. There each time a task completes, we have to set, and we are talking of milliseconds. Just imagine that every millisecond if you need to set the timer, it is a big work, right, if inefficiency. And here, even when the tasks have arbitrary phasing, see, we had seen this simple case, I think this is the one where we had seen here that when we had considered the 0 time, the task P1 has arrived, P2 had arrived with respect to the 0 time and so on. They have kept on repeating here, see here, they have kept on repeating. But what will be the situation? I mean, what will be the period size or the size of the table when the tasks have arbitrary phasings? For example, one task up to some time no event occurred, and then up to some time the task did not arrive at all, and after that time it just kept on recurring every 10 millisecond. And what if another task, nothing was arrived until this time, and then it kept on arriving here. So, what will be the duration for which you need to store the table? Yes, when the tasks have arbitrary phasing,
Highest phase plus
okay. Anybody would like to answer this question? So, I had set this question to one of your predecessor batch, and then said you come up with a proof, and they had actually, some of them had we said that we will give a bonus mark here and you please try this, and then they had come with this. Okay, I think the result is there later. So, they have a proof, nice proof, let us show you, and it remains the LCM P1, P2, Pn. Let us see that. So, before that let us the minor cycle, as we said that typically the major cycle contains an integral number of minor cycle. The minor cycle keeps on repeating, no, it is a periodic timer basically, but it is not compulsory that a major cycle will have an integral number of minor cycle, may not divide that, but we will see that unless it divides, the table size really becomes large, because we can't repeat the table, I mean at the end, until the major and minor cycle are at the same time, complete at the same time, we can't repeat the table. So, the table size becomes very large, it is more than LCM P1, P2, Pn. So, this is the condition I was referring to, that we sometimes have to store the table size more than LCM P1, P2, Pn, and that is this situation. If you have designed a cyclic scheduler where the frame does not divide integrally, does not perfectly divide the major cycle, then we will have to store for the schedule for a much larger time than LCM P1, P2, Pn. So, the frame boundaries are marked through the interrupts of a periodic timer. Now, each task can run in one or more frames, it cannot run in a fraction, I mean it cannot use fraction of a frame and give another frame to some other task, no. It will assign one complete frame or more than one frame to a task, can't give a fraction of a frame to a task. One or more frames is assigned to a task, and we will see that if we are talking of cyclic scheduler, the most important problem before the designer of a real time program is how to find the frame size, the most important question that he has to answer, because this will become the minor cycle, and at this point the tasks will get scheduled. If it is too small, then it will be very bad, totally inefficient. If it is too big, then also it is bad. We have to find out the exact frame size for which it will work. If it is anything other than that, there will be a problem, right, it will be a bad scheduler. So, we will just stop at this point, and we will continue from the next class, that is the important problem of how to select an appropriate frame size here. We will take some example problems here, try to do that, and there are some very important concepts here in designing the actual frame size, and we will also let you do some problems here. We will stop here now.